Failure forecasting boosts robustness of Sim2Real rhythmic insertion policies. This paper addresses the challenges of rhythmic insertion tasks, where a robot must perform precise insertion actions multiple times in succession. A typical example is using a wrench to screw a nut into a bolt. In each round, the robot must align the wrench with the nut, push down, and rotate. And then, it should reset and continue in the next round. There are several major challenges in RIT. First, a millimeter-level accuracy is required for the insertion. Second, in RIT such as screwing a nut, the nut can rotate along the bolt due to friction. Third, the errors accumulate in RIT, and a slight drop of the insertion success rate can lead to a large decline in the overall task performance. To overcome these challenges, we propose a robust single insertion policy and a reliable recovery strategy. Our method consists of 3 modules: a reinforcement learning-based insertion policy, a predefined recovery strategy, and a failure forecasting network. We build the insertion policy by modifying Industrial's coordinate representation from the robot frame to the object's frame. The policy takes as input the wrench's pose in the nut's coordinate frame, and outputs the 6D displacement of the wrench. This object-centric representation significantly improves the Sim2Real transferability. We adopt a simple but effective recovery strategy, lifting the wrench and retrying the insertion. The failure forecasting module continuously monitors the insertion success probability on a history of observations. Once the probability drops below a threshold, it predicts a future failure of the trajectory and triggers the recovery actions. The insertion policy and the failure forecasting model are trained exclusively in simulation and deployed to the real robot in zero-shot. We propose and evaluate 3 failure forecasting models for RIT. All these models were learned from the rollouts generated by the same pre-trained insertion policy. The time-only model triggers a recovery at a fixed time step for different trials. The retry time is determined by the empirical distribution of the rollout's success times. The moving window success model is a trained neural network that estimates the probability of success within a time window in the future. As the time progresses, the observed history gets updated and the prediction window moves along. If the success probability of the window drops below a threshold, the robot lifts the wrench to retry. The previous moving window model focuses on predicting the success time. Instead, this full trajectory success model predicts the success of the trajectory before the maximum termination time. By retrying at an early step, a trajectory can recover from a potential future failure. These videos demonstrate the Sim2Real transferability of the insertion policy with or without the recovery mechanism. We also show the robustness of the system with a learned failure forecasting model in the repeated nut screwing task. The method generalizes to different initial positions and asset dimensions. Our code is open sourced and can be accessed on GitHub.